We now turn our attention to the inverter and battery that will be used in the proposed case solar system at this off-grid telecommunications site. For the inverter, we can assume that it's going to be a 5 kilowatt pure sine wave inverter. So not an inverter charger, just an inverter. For the battery, we're going to assume a lead acid battery, but one of high quality so that it has a long lifetime. We'll assume that it's an industrial AGM or absorbed glass mat battery or gel cell with 2 days of autonomy, so it can run the load for 2 days without any input from the photovoltaic system, starting from a fully charged battery. Pause the video, complete the inverter battery page, and then unpause to see the solution. The first thing I need to do is make the inverter and battery page appear. So up here where I see the plus sign beside inverter and battery, I'm going to add an inverter and battery page here. It pops up with just the inverter cells present. I click on battery to add a battery here as well. For the capacity of the inverter, we know that's 5 kilowatts, so we'll enter that there. For the efficiency, this is a 5 kilowatt inverter with an average load of 1 kilowatt on it. So it's not going to be operating at necessarily its most efficient power level. So I'm going to assume something like 93% here. For miscellaneous losses, I'll leave those at 0. For the initial costs, I'll turn to the cost database. This is a pure sine wave inverter, about 5 kilowatts, so I'll accept that recommendation here to come up with an initial cost for the inverter of about $1,500 US. For the battery, we've been told that it's 2 days of autonomy, meaning it can operate the load for 2 days without input from the photovoltaic array if the battery starts out fully charged. That's actually a reasonably high level of autonomy for this site. Remember, we're on the equator, so there's minimal seasonal variability in the solar radiation, and it's unlikely we're going to have extended periods of time with poor solar availability. So a 2-day battery is relatively large. It should be a relatively reliable system. For the voltage, this is of course a critical parameter in the real world, but in red screen simulation it makes very little difference. So I'm going to put in 96 volts for now, and I'll show you in a bit that that wasn't a critical choice. For the efficiency of the battery, I can turn to the help here and see that the initial suggestion is 85%. Lead acid batteries may be a little bit less efficient than that, but this is a large battery, so the charge currents and discharge currents won't be terribly high, which will improve efficiency. For the maximum depth of discharge, once again, I can turn to help. There's a chart there that helps us out. It suggests that for high quality lead acid photovoltaic or vented batteries, we could have a maximum depth of discharge of 60%. I'm even going to go lower than that. I'm going to go to 80% here. My thinking is that this battery, being relatively large with a relatively good solar resource at the equator, is very rarely going to discharge deeply. So I can permit it from time to time to discharge fairly deeply because the rest of the time it's not going to be discharging deeply at all. For the charge controller efficiency here, I'm going to assume an efficient charge controller. The temperature control method, I'm going to leave that at ambient, indicating we don't have any special method for maintaining the battery temperature. Rather, it's going to more or less track the average air temperature over the course of the day. So that doesn't have much of an impact on the battery capacity because this site is, being on the equator, relatively constant in terms of temperature. There's a suggestion here from RETScreen that the battery should have 751 amp hours of capacity. When we do that, we find a battery with 72.1 kilowatt hours. And I want to show you that if I change this now to 48 volts, the suggested capacity changes here, but in kilowatt hours it's essentially the same size battery, so not a critical choice of parameter. For the initial costs, we can turn to the cost database here and see that for lead acid industrial gel or AGM batteries. Typical installed cost is around $259 per kilowatt hour. So in the absence of a quotation or further information, that'll be my first guess. In the real world, you should definitely dig further, see what real battery costs are going to be. So we end up with the initial costs around $18,679 here. In the next video, we will turn to the photovoltaic array.